Can you hear me now? You should be able to hear me now. I finally got one of those stupid gamer mics, but you have to like tap it to make sure it's on. So it's really easy to not mess up the audio, and I just messed it up. Cool. I'm starting the stream just a little bit early because I can't be late for stuff. It just freaks me out. So I think we'll just chill for a little bit before we get started with the string theory live stream. We'll be continuing what we've been doing last time, going through David Tongs lecture notes. I assume that's available already in the description. Can someone verify that, yes or no? Crabstick, thanks for joining us. Yay, I've been waiting for this next stream. I'm enjoying this so far. This has been a lot of fun. I like keeping it filthy casual. Who was it that said that you learn best when you're smiling? It's like the one instance of telling people they should smile more is like is okay and acceptable. I just like being able to hang out and ask questions myself. I'm not gonna understand everything that I'm reading. Let's video's not very good. Is that true for everybody? Let me switch over to the webcam. The stream's gonna be 2 hours, so I got a hard cutoff at like 4 p.m. Video's good, cool. Live in Flammy's basement? No, he lives in my attic. There's a difference. You see 720p. Should be 1080, but I guess 720 is good enough. Let's go ahead and start some things off. Let's do what we did last time. It looked like people enjoyed the physics hangman. It's a complete shit show. It's awesome with everybody. Airsofters here. That's cool. Let's go ahead. Let's do some hangman. Just we'll do that until like we've got 8 minutes until 2. I don't want to start it before I said that I would. So what's the black thing behind you? This, I went to Home Depot, I picked up some 1-inch foam insulating panel, and then I coated it with some black felt, and then just used like Gorilla Tape on the side so I'd have like a less distracting background for videos. Did not come up with that. I YouTubed partition room dividers do it yourself because they're so expensive on Amazon. Will there be a video from the live stream? Yeah, until I decide exactly what the schedule is going to be for this, it wouldn't be fair for me to be like, well, now it's done forever. Sucks to suck if you didn't make it, you know? So once I can establish when I'll be doing it consistently, then I'll stop uploading the live streams and I'll start only uploading the videos that I'll be making on this stuff. Okay, one sec. Let me switch to the tablet. There we go. Muted. Thank you. Once you switch to the tablet, yeah, I had it on OBS. I had the setting mixed up. I had it turned off. Should be able to hear me now. I see my mom's here. Hey, Mom. Mama says hi. What are you doing? You look like you want to punch me right now, but you won't because you're a cat. Does your cat lift? She plays fetch. Believe that or not. Bhattacharya. That's not the same Bhattacharya who does the GPD calculations, is it, by chance? I don't remember the first name. I need to look this up real quick. Maybe I'll have to do that later. It might just be a a same last name kind of thing. But there's a physicist who is in my field of research. One of the big important objects in nuclear physics are called generalized parton distributions, and there's someone with that last name who's pretty big into that. Andrew, can you do a backflip? No, I can do a front flip. Okay, let's get a quick game of Hangman going. What should we do? I'm gonna do something crazy. This isn't necessarily gonna be string theory related. Let's just draw that, and what should the word be? If you end up enjoy learning from David's notes, do you think you'll go further into more advanced string stuff? From what I've seen, from what I've like skimmed just to see what the timeline is gonna be, I'd really like to delve. The buzzwords that this has made me jump onto and look more has actually been pretty useful for my own research, or for one small aspect, namely the conformal field theory stuff. So I think after this, if I'm not completely satisfied with what I've learned about conformal field theory through these lecture notes, I think I'd like to go deeper into that. Okay, so let's see. Let's do what's a good word? Let's do. I got one. Okay, so this is 3 words if you count the hyphen, making it just 1 word. So let's see a. All right, I see an A. There's definitely an A. I may be spelling this wrong. All right, so I see an A. I see an E. That's the next one I saw. So let's just put up the words. I know that you just do it for when it's wrong, but for me to keep track. There's definitely an E. Okay, I see a C. There's unfortunately no C. I see another C. There's unfortunately not 2 of them. No, I'm just kidding. I'm not going to take off for that. I had to count it though because y'all are going to get it too easily. I see an S. There's no S. Haha. And he's already dead because, joke's on you, this person didn't have arms and legs to begin with, so they've already been hanged. You lose. Just kidding. I see a D. There's no D. I see. What else do we got? I see a C. And I'm trying to just pick these randomly. I promise I'm not choosing the ones that I know aren't working. Maybe I'll do that. Next one I'll choose hopefully one that is working. Okay, I see an N. There you go. Got ourselves a winner, and this is probably going to give it away. Okay. Yeah, y'all got it. You said you can't see the letters? Oh. That's because my face is on it. But yeah, you already got it. Non-abelian. This is where I said I probably didn't spell this right. I always get the A and the U mixed up. Hooray, you all got it. Fantastic. The stream stopped. Is it still going on? Bye, Mom. Thanks for stopping by. Can I explain in simpler methods? I didn't explain anything. This is just Hangman. Non-abelian gauge theory. Yeah. How does curved background Q of T come up in your PhD? What time is it? Okay, we've got 1 minute. I'll do that, and then we'll get into the string theory stuff. So for my research, I'm interested in something called the energy momentum tensor, which is an important object both in quantum field theory and in GR. I mean, it's literally the other side of Einstein's field equations. And when you talk about a quantum field theory, what tells you what you're talking about is when you write down the Lagrangian. Like you could write down a Lagrangian for a scalar field, a real scalar field, say d alpha m squared phi squared minus some interacting potential, or the interaction Lagrangian. In quantum field theory, you can go ahead and start calculating things naively, but you're going to get infinities in your answer. Like, let's pretend that the potential is, let's say that v of phi is some coupling constant phi cubed. You know, you could write down a propagator. You could have something like this, where you have a particle of momentum p going from point x to point y, and you could calculate its matrix elements, 0, phi of y, phi of x. And if you, this would be for like the free propagator, and then if you turn on interactions, then Wick theorem and LSZ tells us that you have to sandwich in the exponential of the interacting Lagrangian, phi of y, exponential I integral d4, let's call it z, the interaction Lagrangian, phi of x, 0. And you expand this exponential. So you could go to order 0th order in the interaction, so you're still considering free field, plus first order, and so on. So if you have phi cubed, this propagator plus its corrections would look like, so that's 0th order, plus something like a self-energy, plus, you know, higher order in lambda. So this would be order lambda to the 4th. When you calculate these higher order things, you get infinities whenever there are loops. So you have to what's called renormalize the theory, which means this is a consequence of your Lagrangian not being in terms of the physical parameters. So that could be your coupling constant, your mass, your fields may not be normalized properly. So you have to renormalize those things. It turns out that when you have an actual operator like the energy momentum tensor, even though you renormalize the theory, you take matrix elements of the energy momentum tensor as an example, there's going to be leftover infinities. There's this whole renormalization of composite operators that's relatively complicated. It turns out in order to remove the infinities for the energy momentum tensor for scalar field theories, you have to first look at how to couple a field, like the scalar field, to a classical curved gravitational background. And that brings you into the idea of something called minimal coupling and non-minimal coupling. So minimal coupling, MC, would be if you write down your action in terms of d4x, and instead of just having it like that, you have the square root of the determinant of the metric for some general curved space metric, and then you have your Lagrangian. That's what you call minimal coupling of the field to gravity. The only thing that quantum field theory knows about gravity for is because of the determinant of the metric. For non-minimal coupling, you have an additional term that directly couples the fields to gravity. You still have that root g, and you still have the L, but you have a direct coupling of the field to gravity through the Ricci scalar. And for some, what you call the non-minimal coupling parameter C. So if you vary this action with respect to the metric, you know, you could be talking about flat space all you want, but if you're taking derivatives with respect to metric components, so in flat space R is 0, but its derivative with respect to the metric is not. And if you vary this thing and you go through with defining some new energy momentum tensor, you get an additional contribution, even in flat space, that renders the matrix elements finite. So in order to get the proper correction to the energy momentum tensor in flat space, you have to derive it from a curved space principle first. So that's the only instance where I have to consider quantum field theory in curved space. Now this isn't quantum gravity because it's still treating gravity classically, but yeah. So I saw a question on that. Thought I'd elaborate a little bit. Then you introduce Fermion Fields and have to do that. Yeah, I actually haven't done that yet for anything more complicated than just a scalar field. I was talking with my advisors about how you would improve the energy momentum tensor if you have additional structure, like you have fermions as well. Wrong, the square root of a negative number does not exist. Come on, basic arithmetic. This isn't the square root of the negative number. The metric determinant is negative, and then you're multiplying that negative by -1. Anyways, I wasted enough time. Let's go ahead and get started with the string theory stuff, shall we? So I'm going to switch screens real quick. I do believe I should be back now. Okay. So, oh yeah, I already had the problem set pulled up. I was trying to remind myself where we left off last time. So let's go ahead and start off. We're on the classical string. We'll start off with the table of contents, I guess, just to remind ourselves of what we went through last time. So this is David Tongs lecture notes. Again, there should be links in the description so that you can follow along or go at your own pace. Let me check these comments to see if anything I said was just people were just saying, I'm a head out or something. Q of t in curved space is awesome. It made me think much more carefully about Q of t in general. Yeah, by the way, when I said that additional term, you can choose C to be whatever you want, and it turns out a particular value of it makes it conformally invariant, which some people argue is like the natural way of lifting to a curved background, is through this non-minimal coupling. Oh, Brahim's here, currently doing research with Andrew in the background. Cool. All right, let's go through this table of contents. How's the audio sound, by the way? With the mic, I assume it should sound better than it usually does. Okay, so last time we went through, let's see, we went through the Y string theory. That took a bit of time, the motivation for it. And then I think we just went through like the action for a point particle. And what else did we do? Should be able to see. Does it look okay? Looks fine to me. Gravity's non-renormalizable. Gravity is subtle. Let's skip on down to where we left off. Yeah, so then we got the string for a point, or the action for a point particle. They talked about reparameterization invariance, which I had to think about a little bit more of what exactly that means. Like if someone doesn't call something that you normally hear it referred to as, you're trying to find out if it's the same thing or not. Because I kept calling it reparameterization rather than like a coordinate transformation, and I wasn't sure exactly how those things were different. I think when they're talking about the action being reparameterization invariant, like you see these tick marks along here that we're integrating over. At the end, the action does not depend on how we space the tick marks, or if the spacing of the tick marks is a function of some other parameter parameterizing this path, any point along this path. And eventually we're adding it all up, so our choice of how we're stepping along here doesn't matter because we're adding it up at the end anyways. I think that's what it's just referring to, is the end result doesn't depend on it. But diffeomorphism invariance is what someone said. Again, yeah, like I think that was my question last time, is someone said, because I understand diffeomorphisms just as like general coordinate transformations. Yeah, anyways. So this was just the point particle, then they expressed it in a covariant way, which bought ourselves some redundant degrees of freedom that were non-physical. Or you can't invent more degrees of freedom. So if we express things in the language of 4 vectors, those degrees of freedom should be fixed by some constraint, and that constraint ended up being the mass shell relation. This is the constraint on the system. It's, of course, it tells us that the particle isn't allowed to sit still in Minkowski space. It at least has to move through time. Any real particle satisfies this. And they described Poincare symmetry. So we have Lorentz transformations plus translations. We have made all the symmetries manifest at the price of introducing a gauge symmetry into our system. A similar gauge symmetry will arise in the relativistic string, and much of this course will be devoted to understanding its consequences. Okay, so this is, I think, more or less where we left off, and we did that one problem where we did like the equation of motion stuff. We did the problem, but we hadn't even really gotten to the lecture note part yet. I think we had to look. But now that brings us to quantization. Does that sound good? Why did you choose these lectures particularly, or are you just going through them because it was your first find? No, this is what came highly recommended. I mean, you're never going to find out everything from one source. I don't think anyone goes into something expecting that, but this just came in pretty high regard, and that there were recommendations for more advanced topics that you could go through with this, which I'm not up for yet, so it doesn't really apply to me. Okay. Is that the Schrodinger equation with proper time tau? Excellent question. Let's find out. So we're starting with quantization. It's a trivial matter to quantize this action. So with this action, they're talking about this one here. And this isn't unique to string theory. This is what you kind of do. The action is basically the proper time. If you take a course in GR, this is just what you do. Okay, so they define the canonical momentum from this, and then we go down to here. Okay, so now we're going to go into like a Hamiltonian formalism, I suppose. It's a trivial matter to quantize the action. We introduce a wave function psi. This satisfies the usual Schrodinger equation, but computing the Hamiltonian, x dot mu contracted with the momentum minus the Lagrangian, we find that it vanishes. H equals 0. So we can take p mu and use this relation here. So we can write it in terms of x dot and then contract that with this, where is it? With this x dot, and subtract from that the Lagrangian inside of this action integral, and I guess we just get 0. That's just a matter of the algebra. I don't think there's anything too... I mean, the fact that the Hamiltonian 0 is interesting, but showing that is probably not hard. This shouldn't be surprising. Okay, well, I just called it interesting, so maybe that's embarrassing. This shouldn't be surprising. It's simply telling us that the wave function doesn't depend on tau. Why? I'm thinking in terms of chain rule, and I think I shouldn't be, because I'm thinking if I take a derivative with respect to tau, I could just as easily write that as dt tau is equal to dt d tau ddt. And if I differentiate the wave function with respect to time, is that the reparameterization invariance? That's probably what it is. I need to get through my head that the tau is not something physical here. It's simply telling us the wave function doesn't depend on tau. Since the wave function is something physical, as we've seen, tau is not. This is to be expected. Note that this doesn't mean that the time has dropped out. Okay, so this should hopefully answer my question or address my confusion. On the contrary, in this relativistic context, x0 is an operator, just like the spatial coordinates x. This means that the wave function is immediately a function of space and time. It is not like a static state in quantum mechanics, but the fully integrated solution to the non-relativistic Schrodinger equation. Is there a relativistic Schrodinger equation? Oh, are they just going to say it's the Klein-Gordon equation? The classical system has a constraint given by 1.5. In the quantum theory, we impose this constraint as an operator equation. Right. Okay, so that's what they're saying. So if you take... You have the standard, like the energy operator is proportional to a time derivative, and the momentum operator is proportional to a spatial derivative, which they gather collectively into what they're calling p mu. Now, if you square this, so p mu plus mass, and then you have all of that acting on a wave function. So you substitute in this derivative, this operator substitution in for the momentum, and that's just going to give you the Klein-Gordon equation. It gives you the wave equation, right? So if you've heard of the Klein-Gordon equation but haven't seen it derived, it's pretty straightforward. You literally substitute this in, and then if you want to get to the Dirac equation, you sort of factor it. Although this equation is familiar from field theory, it's important to realize that the interpretation is somewhat different. In relativistic field theory, the Klein-Gordon equation, so if they're talking about field theory, like a relativistic field theory, that could just be E and M. And if you take Maxwell's equations and you form those various like double products involving the derivatives, you can derive the wave equation. You can derive this equation from Maxwell's equations is what I'm getting at. And that's classical. Instead of a wave function, you'd have like E and B fields or whatever. Yeah, I think that's right. Yeah. But in relativistic field theory, the Klein-Gordon equation is the equation of motion obeyed by a scalar field. In relativistic quantum mechanics, it's the equation obeyed by the wave function. Right? In the early days of field theory, the fact that these two equations are the same led people to think one should view the wave function as a classical field and quantize it a second time. So, I actually didn't know that that's where the terminology came from. This isn't correct, but nonetheless the language is stuck, and it's common to talk about the point-particle perspective as first quantization and the field theory perspective as second quantization. Right. So I've always just thought of second quantization. Like in first quantization, your observables are replaced with differential operators, and in second quantization, your fields are also promoted to operators. That is if you're taking the canonical quantization approach, not the path integral. But will I be able to compete with Papa Flammy? Compete in what? So the wave function and a scalar field are the same thing. Scalar, no, I wouldn't say that at all. For one, the wave function, a scalar field, when you call something a scalar, you should be talking about, the context should tell you scalar under what kind of transformations. And I don't think anyone would claim that the wave function is invariant under Lorentz transformations. But they're pointing out similarities. Okay. Although this equation, we already read that, didn't we? So far, we've only considered a point particle. How can we introduce interactions into this framework? Right. So far, we only have free particles, nothing tugging on them. How can we introduce interactions into this framework? We would have to first decide what interactions are allowed. Perhaps the particle can split into two. That's a weird way of thinking about it to me. Obviously, there's a huge range of options for us to choose from. We would then assign amplitudes for these processes to happen. There would be certain restrictions coming from the requirement of unitarity. Those of you who are unfamiliar, unitarity is related to conservation of probability. Probability should add up to 1. You're not saying everything should have 100% probability, but you'll find as it goes that perturbative string theory is actually first quantized. It can be second quantized, but the string field theory is very specialized and very hard. So does that mean that you would do these perturbative string theory calculations in like a path integral framework? What are these 1, 2s, and 3s? 1 in chat for physicists, 2 for engineers. Okay. among other things, would lead to the necessity of antiparticles. We could draw diagrams associated to the different interactions, as an example given in the figure, and in this manner we would slowly build up the Feynman expansion that is familiar from field theory. This is what Feynman did for QED. However, in practice, we rarely construct particle interactions in this way because the field theory framework provides a much, better way of looking at things. That didn't really seem to... I'm sure it makes sense. I don't understand that exactly. I mean, I'm just used to... I'm not used to asking what's allowed. I'm used to just doing the calculation, right? The Wick theorem and the rules for contracting fields with other fields or fields with external states or whatever kind of tells you what's allowed. I'm not quite sure what insight that's supposed to give. Andrew, any tips on transitioning from special relativity to GR? I guess it depends. When you learned special relativity, did you just keep it in terms of regular algebra, or did you introduce tensors at all? If you understand how to manipulate tensor indices without really having to think too much, it's kind of like when Goku and Gohan were in the hyperbolic time chamber and they insisted on staying Super Saiyans. That way, that was basically their new base form. They didn't have to waste any energy doing that. That way, if they had to push themselves further, that was natural. That's kind of like learning tensors and wanting to go into GR. Like if you're going through GR and trying to wrap your head around the physics and you're trying to grapple with the tensor indices, it'd be very easy to get lost. So familiarizing yourselves with tensor analysis is invaluable. If not through my videos, Chris has great videos on it. Anyways, let's try to get a little bit farther. So they're saying, in practice, we don't construct particle interactions this way. Field theory is better. In contrast, this way of building up interactions is what we will later do for strings. Okay, that's good, because I don't really know what they're talking about there. You introduce an interaction Lagrangian, and that kind of tells you what you're allowed to do. Like if you have phi cubed, your vertices have 3 lines leading to them, right? Phi to the 4 theory, your vertices have 4 lines. I'm not entirely sure. Okay, there's another action that describes the relativistic point particle. We introduce yet another field on the world line, E of tau. So this is something we encountered when we were tackling that problem set last time, where we used the equations of motion to arrive at the other form of the action. X dot squared is just the contraction of those two x dots with the Minkowski metric. This form of the action makes it look as if we've coupled the world line theory to a one-dimensional gravity. I mean, it looks like you've coupled it to a one-dimensional something. I'm not quite sure. How do you know? Why does that tell me that it has to be gravity? World line theory, one-dimensional gravity with the field E of tau acting as an Einbein in the sense of 4 beans that were introduced in GR. Oh, okay. I think I kind of get it. To see this, note that we can change notation and write it this way. Got it. So this is analogous to what I was writing down earlier about quantum field theory in curved spacetime. I think, right? Einbein sounds kind of funny. It can easily be checked, so it gives the same equation of motion because it has this E is completely determined by this equation of motion. Right, we were able to get to that point really easily because there were no derivatives of the fields here, of E here, with respect to tau. So that made writing down the equations of motion easy. Then we substituted that into this action, and after someone pointed out my missing minus sign, then we got the right answer. Okay, the action in 1.8 has a couple of advantages. It works for massless particles for m equal to 0. How did that get by me? That's cool. Secondly, the absence of the annoying square root means that it's easier to quantize in a path integral framework. I don't know about path integrals for that. I'm not too familiar with square roots. Is it like a measure? Like the problem with path integrals is always the integration measure, right? Is that the issue there? Because the only issue I see with square roots in quantum field theory, let me go ahead and try to switch. I'm going to go on over to my tablet real quick. The only thing I can think of where square roots in quantum field theory become annoying, not necessarily like wrong or something, but just annoying, would be if you're considering like Fourier transforms, where you'll have this square root d, I don't know, let's just call it dnx, because I don't quite remember what the dimensionality is. Then there's probably like a 2 pi to the n, and then there's a twice the energy term times whatever you're doing the Fourier transform of. And if you substitute in the dispersion relation, we have E is equal to the square root of m squared plus p squared, where c is 1. And then you do the first quantization where your momentum becomes a differential operator, then this becomes something like a square root m squared plus, or I guess it would be minus something that's proportional to second derivative. So how do you take derivatives when the derivative's in the square root like this? So you have to expand the square root. So those, in certain contexts, you'll see that referred to as relativistic corrections on where you truncate that series at. So that's where I've seen square roots be annoying, but I'm not really familiar with it giving problems in path integral. Then again, I don't do calculations using the path integral, so maybe there you go. Okay. Maybe someone in the comments is enlightening me right now. What's wrong with path integrals and square roots? What am I not thinking of? Oh, so Airsofter says you're right about the Fourier transform, but you also can't complete the square trick to get the correlation functions. I see. I see. Oh, we've got a German boy in the chat. God, what is with flammable mats and sauerkraut? Am I right, guys? Yes, I will upload the stream later. Once I have a set schedule for these streams, I'll stop doing that because you'll know when they're happening. But in the meantime, yeah, this is gonna be uploaded. As long as I don't do an oopsie. Okay. Action retains invariance under reparameterizations. It's the same action, right? So if the action is reparameterization invariant, then writing it a different way, why would it lose that? I don't know. For transformations parameterized by an infinitesimal eta, these are the transformations of tau, the field, and the coordinates. The Einbein, the four beans transform as a density under the world line, while each of the coordinates transforms as a world line scalar. Let's think about that. Yeah, if you guys are new to this stream, you're gonna see me having to ask a lot of questions and think this stuff out because your boy's a little slow. Hold on, they're saying the density part makes sense to me. I'm not sure I get the world line scalar for the coordinates because usually I mean, if you have a coordinate x in some prime frame x prime mu, it's defined to be a vector. So in some unprimed frame, it would transform in the following way. Prime mu dx nu. That's not a scalar, unless those transformation coefficients are just 1. I guess there's nothing wrong with that. That could be it. They transform trivially, I guess in this case. And then they're saying that E transforms as a density. That's not too surprising either, because that's kind of, it looks like it's serving the role as the determinant of the metric. And if you were to have something like dx, dy, dz in one basis, and you write it in, say, spherical coordinates or something, so you have your dr, d theta, d phi, that's not the transformation. That's not how you transform these volume elements. You need that Jacobian factor, where j is your, r squared sine theta. It turns out that this r squared sine, it turns out that this Jacobian transforms, and it is basically the determinant of the metric. If you look at how the second rank tensor transforms and let the tensor be the metric, and then take the determinant of both sides, you see that it ends up being the Jacobian. So this integration measure transforms as a density. So E, I see how that would transform as a density as well. So I think that makes sense to me. So you're saying you're thinking about how X transforms under space-time transformations. They're talking about how it transforms under world line transformations. What if I just left there? It's like, okay, I quit. World line transformations. World line transformations. So like deforming the world line, or what? What does that mean? X mu still transforms as a vector in space-time, transforms as a scalar under the world line to single coordinate tau. Oh, okay. I think that makes more sense to me. Cool. Thank you. It's good having Airsofter here. For the record, I kind of moved the stream to earlier here just so that there would be a chance that you'd come to tell me when I don't understand something. Nambugato action. So now we're moving on to something else, I guess. The particle sweeps out a world line in Minkowski space. A string sweeps out a world sheet. We'll parameterize. Oh, so you have the string and then going through time. So you get a two-dimensional surface, I guess embedded in a four-dimensional space-time. We'll parameterize this world sheet one time-like coordinate tau and one space-like coordinate sigma. In this section, we'll focus on closed strings and take sigma to be periodic. So sigma is like an angle, 0 to 2 pi, so you probably have like periodic boundary conditions. Sometimes we'll package the two world sheet coordinates together as sigma alpha. What the hell? Jesus. All right. I think I might have to mute some of you if you keep writing. It's very cool that you're class 9. Okay. Is it chilling out? Maybe put you guys in timeout. Okay. Back to the action. Okay, so yeah. What does this say? We will sometimes package the two. So alpha goes 0 to 1. So yeah, we have this two-dimensional surface. The string sweeps out a surface, which defines a map from the world sheet to Minkowski space. For closed strings, we require... So this is a coordinate, is x mu. X mu is some coordinate 4 vector that describes any point in Minkowski space, and we're saying it's a function of those two parameters. Okay. Sorry, I'm just removing some people. Should help a little bit. But is that right? So we have x mu is talking about any point in Minkowski space, and that 4 vector is like each component of that 4 vector is a function of sigma and tau. Is that right? X mu parameterizes the world sheet of the string embedded in spacetime. Okay. In this context, it's sometimes referred to as the target space to distinguish it from the world sheet. We need an action that describes the dynamics of the string. So let me think about that. We need an action that describes the dynamics. Well, what's the difference between a string and a point particle? So, oh, well, in one, we just had one free parameter, this tau, and now we also have the additional degree of freedom. We have this sigma, so it's just going to be like a two-dimensional integral or something. The key property that we will ask for is that nothing depends on the coordinates sigma alpha that we chose on the world sheet. In other words, the string action should be reparameterization invariant. I think I hate that word. I don't know why I hate that word so much. What kind of action does this trick? Well, for the point particle, the action was proportional to the length of the world line. The obvious generalization is that the action for the string should be proportional to the area. Okay, so yeah, I guess that's just going from d tau to d tau d sigma or something. This is certainly a property that is characteristic of the world sheet itself rather than any choice of parameterization. How do we find the area in terms of coordinates? The world sheet is a curved surface embedded in spacetime. The induced metric on this surface, we're going to run into a lot of terminology that I've seen before, but I don't really know what it means. I've seen the term induced metric and the pullback. Is that like a projection? So if you have like I don't know, if you have a two-dimensional, like a surface of a sphere embedded in a three-dimensional space, is it some way of like acting on that three-dimensional Euclidean space and getting a two-dimensional sphere, like the metric for the surface of the sphere out of it? Is that what that is? Okay. The induced metric is the pullback. I think it's like a metric due to another metric. It's a map between two manifolds that can take points or vectors. Oh, Eigenkris is here. I think you're right. If a sphere lives in 3D space, the induced metric is the 2x2 metric for measuring length on the sphere that you get from the ambient metric of three-dimensional space. You can kind of think of pullbacks as a projection for these purposes. It's formally to do with maps between manifolds and how metric go the other way between a map. So maybe I'm not formally correct, but if I have like a larger space like R3 and I act on it with some transformation matrices, so I guess it wouldn't be a square matrix that would spit out a two-dimensional metric for like the surface of a sphere or whatever, like a subspace of R3. Maybe that's not correct, but let's just move on from that, I guess. The induced metric on the surface, well, I guess they have the definition. We can see what this means. The induced metric on this surface is the pullback of the flat metric on the Minkowski space. So we have d mu, d sigma alpha. Let's take a look at this real quick. Time is it? Are we doing all right? Yeah, we're doing plenty fine. I'm going to switch over to the tablet. So they define they're defining this pullback of the flat metric. Let's get everything accounted for. So they define some sigma alpha, which is just tau and sigma, and alpha. So alpha goes from 1 to 2. Then we also have x mu, which is a function, I guess, of sigma alpha. And then they're defining the pullback gamma alpha beta is equal to dx mu d sigma alpha. Yeah, so this would be, it would not be just a square matrix then, I suppose, right? dx, or gamma is going to be 1, but I don't think the transformation coefficients would be. Dx nu, dx, or d sigma beta. Then Minkowski, so eta mu nu. So I don't know if this is going to tell. So we could pick out components if we wanted to. We could do like dx mu d sigma 1, which would just be like x dot mu d sigma mu d sigma 1. That would be something like a gradient, I guess. Well, not really, because that's just kind of what it is. I don't know how to shorthand that any better way. It be what it be. Yeah, I don't know if this is going to be helpful for me. But I think that does kind of answer my question about we do have like this square matrix. Here, let me let's go ahead and remove some people. Yeah, sorry. I'll try to keep a better eye on the chat to make sure this doesn't happen. I guess in the future I should probably have some mods that could do this better. Andrew, you can look up these definitions in a standard smooth manifolds book, like Introduction to Smooth Manifolds by Lee. Okay. You need to substitute x mu to x mu sigma alpha into the Minkowski metric to get the induced metric. Okay, I think that makes sense. Okay. Moving on. You write about how the pullback of the metric can give a metric on a subspace. This is covered quite nicely in his GR notes. So in other words, you're saying this is something I should already know. Okay. Where were we? They defined this pullback. Then the action, which is proportional to the area of the world sheet, is given by the determinant of the pullback metric. So dynamics, if we have this two-dimensional area that's kind of evolving in tau, we're talking about areas changing then in a sense. So the action being in terms of this determinant of the metric, which would tell you how these volume elements, or I guess in this case these area elements, are changing. That sounds reasonable, that the dynamics would be of something having to do with the area of the world sheet being related to the determinant of the metric, which talks about how areas transform. I'll buy that. Aha. Oh, wait. Oh, Airsoft, I'm just giving you a hard time. I know you weren't saying that. Granted, I mean, the GR, when I first learned it informally, I pulled from so many different sources, and it was informal, so I had several holes, and then when I actually took it in graduate level, it was through Hartle's book, which I'm not a huge fan of, because he waits until like the last page to introduce what a tensor is. But okay. Then the action proportional to the area of the world sheet is given by some constant times this integral. T is a constant of proportionality. We'll see that it corresponds to the tension of the string. So the whole thing would have units of area then, if it's two-dimensional. Well, tau's probably dimensionless, so maybe I'm confusing myself. We can write this action, so they do actually gather the components in the matrix element of this pullback. So it's symmetric, which is expected. Okay. The action then takes this form. So they're taking the determinant of this. So you got cross minus cross, which is just this guy here. And I guess this is called the Nambu-Gato action for the relativistic string. Okay, fantastic. So far, so good. That's not too bad. Okay, moving on. Action equals area. I don't think we have to do that. That's it looks short. Okay, they're taking the tangent vectors, forming the scalar product, and you get the same thing. Right. Tension and dimension. Let's now see that T has the physical interpretation of tension. I'm glad they weren't like, by the way, it's just tension, believe us. Okay, so let's see why that this is tension. I assume it's just dimensional analysis. We write Minkowski coordinates as x mu is equal to t x vector. We work in a gauge where x0 is equal to t, which is equal to r times tau. It's a constant that is needed to balance dimensions, and will drop out at the end of the argument. Consider a snapshot of a string configuration at a time when dx d tau equals 0. So at a point, so maybe it's changing directions or something, and at the turning point is where they're talking about this, so that there's no kinetic energy. Evaluating the action for a time d tau. So we just have a potential term. R dx d sigma squared. And then they substitute in r times d tau is just dt. And then you have d sigma times the square root has something like a length of the string. So the action has units of length of the string times tau, or sorry, times t. But when the kinetic energy vanishes, the action is proportional to the time integral of the potential energy. Right, so unit-wise, we have potential energy. The time integral. So now they're just comparing integrands. Potential energy equals t times spatial length. So if you divide both sides, potential energy over time. Potential energy over length. Energy over length. Okay, so that would be something like a force. So T is indeed the energy per unit length as claimed. Okay. That seems a little heuristic. Is that the best way to show that? Because it seems like I'll buy that it definitely would have units of force, but is it... What tells me it's at tension? I mean, I guess it's energy per length of the string. Oh, yeah, okay, if it's potential energy per length of the string, yeah, okay, that would make sense. And if you stretch or compress the string, like if it's elastic, how would that affect the tension? We learned that the string acts rather like an elastic band and its energy increases linearly with length. This is different from elastic bands you're used to, which obey Hooke's law. There you go, for my introductory physics people in here. Hooke's law is coming back. Well, I guess they're saying it's not, because Hooke's law, you would say that the force is linear. The energy would be quadratic. So that's the difference. Is here the energy increases linearly. To minimize its potential energy, the string would want to shrink to zero size. Quantum effects make this not happen because zero-point energy is a thing that exists. How convenient. There's a slightly annoying way of writing the tension that has its origin in ancient history, but it's commonly used today. T is equal to 1 over 2 pi alpha prime. It's referred to as the universal Regis slope. So is this a callback to when I'm not really familiar with Regis theory, but I know there was something about if you had before QCD, if you talked about quarks being confined inside the proton having a very high energy, but they're confined to something so small, then they must be rotating at close to the speed of light. Is that tension related to that? I wonder. Am I missing something? I wouldn't take the tension argument too seriously. It's a free parameter. It has the right units. Regis slope equals Regis trajectories equals quark-antiquark pairs with high angular momentum. Okay, so it is the same. Okay. Every time we get through a paragraph without having to go back to the tablet, I'm like, okay, cool, we're moving along. This is nice. At this point, it's worth pointing out some conventions that we have, until now, left implicit. Space-time coordinates have dimension -1. I assume this is mass dimensions. So if we're using natural units, then energy has units of mass. Those have the same units. Maybe it's easier to write this out. I don't want to lose people. Just talked about not going to the tablet. I think that this is what they're saying. So if you were to write down the on the mass shell relation, E squared is equal to m squared plus p squared, which is in units where c is equal to 1, then things like energy, mass, and momentum all have the same units. We say they have the same mass dimension. If you say mass dimension 1. And then you can write down like a ds squared equals, whoops. And you can show that in the system of units, time and space then have the same units, which are the inverse units of mass and energy. So if you say that the units of energy or the units have the mass dimension of mass, which have the mass dimension of momentum, equal 1, then you would do the same thing for space and time. So you would say t mass dimensions of x, which would equal -1. This is kind of related to the statement that this inverse relation of the units kind of goes with saying that if you want to probe very small size scales, you need very high energy. This inverse relation between the units. Don't take that too literally, but that's one way of looking at it. Is there anything else I wanted to say with that? And if one thing that you could do with this is if you say that the action in the system of units is dimensionless, if h bar and c are 1, then you can play with what the dimensions of the field have to be, what the coupling have to be. So I think this is just the general mass dimension arguments that you do. Does the tension part even matter for the purposes of the Euler-Lagrange equation? That's a good question, because if it's a constant, then a constant times something extremized is going to give you the same equations of motion. That's a good question. And Airsofter had a response. It doesn't, but it will matter in quantum theory. Okay. Let's move along. It's pointing out some conventions. We read that part. In contrast, world sheet coordinates are dimensionless. Yeah, because this is like an angle. Tension is equal to mass per unit length. Has dimension 2. Obviously, this means alpha prime. I don't really get the point of this. I see how it's right, but I'm not quite sure what the insight is here. The string scale, maybe that's what it is the natural length that appears in string theory. In fact, in a certain sense, this length scale is the only parameter of the theory. So in the Lagrangian, you would have a mass term, and you're saying the mass is determined by the tension, and the tension is determined by this length scale or something. And then I imagine they're going to have to, there's coupling constants depending on what field theory you're talking about. So I don't know if they're saying we're getting rid of coupling constants, or the coupling constants can be expressed in terms of this parameter as well. It's not immediately clear to me how that happens, but what's amazing in string theory is that all the couplings are determined by the dynamics. You don't have freedom of adjusting them. So you don't have to renormalize? What does that mean? That's weird. Maybe we're getting ahead of ourselves. Let's just keep pressing on. Or is it like GR, where it's like you don't have this force, of gravity influencing the particle's behavior. The particle is behaving as a free particle just in a curved space. Is that it, or something? There are no coupling constants in string theory. The ones resulting in the effective actions are dynamical. There are steps. So now we're going from actual strings versus fundamental strings. Okay. There are several situations in nature where string-like objects arise. What time is it? So we got another hour. Prime examples are like magnetic flux tubes and superconductors, or chromoelectric flux tubes in QCD. Cosmic strings. I think I saw that one, what was it? 60 Symbols video of that one guy that everyone loves because he's very lovable, talking about cosmic strings. A popular speculation in cosmology are similar objects stretched across the sky. In each of these situations, there are typically two length scales associated to the string, the tension and the width. So we're treating this string as one-dimensional then. Typically be additional terms in the action that depend on the width. The string scale, the tension depends on the kind of string that we're considering. We're considering QCD flux tubes. We would do that. This was, of course, well, yeah, in this course we will consider fundamental strings have zero width. This means in practice is what we take the Nambu-Gato action as the complete description for all configurations. Okay, so you can make things more complicated. Fantastic. However, I should point out that when we tried to view string theory as a fundamental theory of quantum gravity, we don't really know what value t should take. As we will see later in the course, it depends on many other aspects, most notably the string coupling and the volume of the extra dimensions. It's a weird thing to think about. Symmetries of the Nambu-Gato action. two types of symmetry, each of a different nature. Let's see if we can guess. What should the action be? What should the symmetry be? It should probably be invariant under general coordinate transformations, and I bet you the stupid reparameterization invariance is going to be the other one. Poincare invariance, close enough. This is a global symmetry from the perspective of the world sheet. That means lambda mu nu and c mu, which label those symmetry transformations, are constant and do not depend on the world sheet coordinates. Let me read that one more time. I went a little fast. It's a global symmetry. Okay. So we're not letting lambda mu nu or c mu depend on those coordinates. That's what they mean by global. Reparameterization invariance. As for the point particle, this is a gauge symmetry. It reflects that we have a redundancy in our description. Okay. That kind of argument is it's gonna confuse me throughout this, because I get that if it's not physical, the end result shouldn't depend on it, like the action or something, or as a consequence, equations of motion. But intermediate calculational steps, I don't see why they couldn't. Right? If it's not measurable, why can't the thing that's not measurable depend on your choice of parameterization? Maybe it still does. I assume it probably still does, and it's just the physical things are going to be, once the dust settles and you calculate something physical, your choice of parameterization is going to cancel out. Just like any you calculate a scattering amplitude, your gauge, how do I say this? Whatever you're using to parameterize your gauge transformation should not show up in your cross-section calculation. It shouldn't matter. String isn't that thing that spiders drop and you can make wool and bows and stuff. Exactly. That's exactly what it is. String theory is perturbation theory around a fixed space-time background, so the general covariance is not imposed as a global symmetry, but should pop out when you include graviton strings. The problem is that when you have to deal, the problem is that you will have to deal with it as a gauge theory when you quantize it with path integrals. As a result, he's being very careful about it when he introduces it. Okay. Where are we? These look like canonical momentum or something. Momenta, which we'll call pi, because there will be countless other quantities that we want to call p later. So they're just taking the action and they're going to write down the equations of motion. There are two parameters. These look like nasty nonlinear equations. Yeah, taking derivatives of this mess with respect to tau and with respect to sigma. There's a slightly nicer way to write these equations. Starting from the earlier action, recall that the variation of the determinant of the metric I'm used to a minus sign being there, but okay. Using the definition of the pullback metric, this gives rise to the equations of motion here. Okay, so this looks like the definition of the covariant Laplacian, but missing an extra factor of that determinant. Actually, I think that's exactly what this is, because there's usually a 1 over root g here, and then you have derivative, determinant of the metric, the actual metric, derivative. Yeah, so this is like the covariant version of the wave equation. Right? Unless I'm reading that wrong. No, I think that's right. Okay, well, I mean that's satisfying to make sure that when we write down equations of motion for something that's like a free particle, then we get something familiar. This may not look familiar to some of you, but this is just, if you write down if you swap out partial derivatives for covariant derivatives and then do the tensor index manipulation, this is almost the covariant Laplacian. Okay. Although this notation makes the equations look nicer, we're still kidding ourselves. It's still a Laplacian. Written in terms of x mu, they're still the same equations. Still nasty. So now we're moving on to the Polyakov action. The square root in the Nambu-Gato action means that it's difficult to quantize using path integral techniques. However, there's another form. There is another form of the string action, which is classically equivalent. It eliminates the square root at the expense of introducing another field. So what do we have here? We have that antiquated tension definition thing. We have d squared sigma d alpha x mu d beta x nu. So that's just like the kinetic term in the Klein-Gordon action for a particular mu and nu. And g alpha beta, so that, wait a second. Yes, okay. Yeah, that, it's a little weird to me, see, like, because it's not just a scalar field, it's a vector field x mu, but same, it looks very similar to like the Klein-Gordon action for a massless particle. This is the Polyakov action. He didn't discover it, but he understood how to work with it in the path integral, and for this reason it carries his name. I'll have to keep that, I'll have to remember that. The path integral treatment of this action will be the subject of Chapter 5. The new field is G alpha beta. It's a dynamical metric on the worldsheet. From the perspective of the worldsheet, the Polyakov action is a bunch of scalar fields x coupled to a two-dimensional gravity. The equation of motion is basically the same. Yeah, it's the same, but instead of the pullback metric, you have the, I guess, this dynamical metric, which coincides with the equations of motion 1.21. To determine this, we vary the action. Right. I'm trying to point out when I don't understand things, and I'm trying to point out when things aren't unique to this, right? If these pop up a lot of other places, like these little identities, this variation of the determinant, you want to calculate what the energy momentum tensor is for a given Lagrangian using Einstein's definition of varying the action with respect to the metric components. It's like things like this pop up. It's not just string stuff. So the varying the action, and what are our degrees? What are our degrees of freedom? We have this new metric, and I guess x mu. So when we vary the action, we have delta g alpha beta. Is that it? Are we not varying it with respect to x mu? Well, I guess that would just give you would get two equations of motion, one for x and one for g mu nu, and doing it with respect to g mu nu should just give you the field equations, right? Probably, maybe not. The metric is 2 times a function of sigma d alpha x d beta x, where the function is given by what is going on, man? What's with the spam today? Yeah, there's no Ricci scalar term, so you don't exactly get, yeah. Okay. I'm trying to pick out the useful information here with this Polyakov action. They're saying it reduces to the same action classically as the Nambu-Gato action, I believe. It coincides with the equation of motion 1.21. Like I said, this is basically the same equation, but just with a different metric. It's an independent variable with its own equation of motion. Okay. A comment on the potentially ambiguous notation. Here and below, any function f of sigma is always shorthand for f of sigma tau. It in no way implies that f depends only on the spatial coordinates. Okay. We see that g alpha beta isn't quite the same as the pullback. The two differ by the conformal factor f. Right. This doesn't matter because, rather remarkably, f drops out of the equation of motion. Even though f isn't a constant, it's a local. The conformal factor is local. That is interesting. Okay. That doesn't sound easy to prove, though. We therefore see that the non-Bugado action and the Polyakov action results in the same equation of motion for x. This would probably be a good exercise to go through, but I don't know if I'll do it here. I don't know if I'll try to do it here anyways. Okay. You should have some mods. I'd gladly volunteer. I'll take you up on that, actually. I think I will, because I keep looking away, and then it gets crazy. Is Airsofter still here? I trust him. Or anyone else? Not anyone else, as in, like, I don't trust you. Airsofter, do you mind modding a little bit? Not to put you on the spot, but I'm going to put you on the spot. How about this? I'll make you a mod, and then if you'd like to help out, that would be appreciated, depending on how long you can stay for. But I know it's late where you are. Okay. Where are we? Yeah, this would be a good. This sounds like a good exercise. I bet that's one of the exercises, actually. In fact, we can see more directly that the actions coincide. We can replace this with its equation of motion. Ah. Maybe that's not too hard then. Okay, let's talk about symmetries of the Polyakov action. The fact that the presence of the factor f of sigma tau didn't actually affect the equations of motion reflects the existence of an extra symmetry, which the Polyakov action enjoys. Well, considering it was a conformal factor, I imagine it's going to be conformal invariance. So it still has Poincare invariance, reparameterization invariance, also known as diffeomorphism. So you guys were right when I was asking what it was, and you said it was just these guys. This is a gauge symmetry. We may redefine the worldsheet coordinates. The fields transform as scalars, while g alpha beta transforms in the manner appropriate for a two-dimensional metric. It will sometimes be useful to work infinitesimally. If we make the coordinate change, the transformations of the fields. Okay. For the covariant derivative. Usual expression. Yeah. Together with these familiar symmetries, I guess for those of you who aren't really familiar with GR, when you talk about how vectors change, they can change in more than one way. They can change because their components are changing, so you can change by taking the derivative of the vector itself, but a vector can also change because the basis vectors are changing. Like if you have the vector on the surface of the sphere and you're moving it around, then those basis vectors are changing direction, so the vector changes two ways. Just taking the regular partial derivative only accounts for case number 1, where it's the vector components that are changing. Case number 2 is addressed by introducing these Levi-Civita connections or Christoffel symbols that take into account how the basis vectors change. In curved space, that's not quite an appropriate way to think about them, but in flat space, that's fine. Together with these familiar symmetries, there's a new symmetry which is novel, while invariance. Okay, I always get these confused. I say always as if it's something I've been thinking about forever. Conformal transformations are actually relatively new to me. But when people talk about like while invariance plus diffeomorphism invariance implying conformal invariance, or that stuff always confuses me because people have a tendency to use the term conformal transformation and while transformation and scale transformation interchangeably, and I'm not quite sold on which one is which yet. Under this symmetry, the fields are left unchanged, or these x mu's are left unchanged, sorry, while the metric changes. Okay, so they're saying for the while change, the while transformation, it's a transformation of the metric itself, but we're leaving the coordinates alone. That's how okay, so what I was calling conformal transformations, I should have called while transformations, I suppose. Okay. Going to go through some of these comments real quick. While invariance and conformal invariance are very closely related. Conformal transformation equals a local scaling. The defining aspect is that it conserves angles. I'm not used to so much spam on the channel. I don't really get it. Conformal transformation is a transformation of coordinates, so it's not just a transformation of the fields. Someone says gauge fixed is actually right. I would say be careful. Everyone confuses while and conformal invariance. I'm aware. I must have like 15 tabs open actually on conformal transformations. And they all say something different. Okay, so we're having this local rescaling of the metric. Or infinitesimally, we can write omega squared as some exponential for small phi. Okay, yeah. So it would be 1 plus, so you're expanding this exponential. So it would be the regular metric plus a small deviation, which would be 2 phi. Yeah, 2 phi times the metric. So that's what they're calling delta. It's simple to see that the Polyakov action is invariant under this transformation. The factors of omega squared drop out just as the factors of f did. That's really interesting to me because if you look at if we go back to the equations of motion, yeah, if we go back to this equation of motion, like, let me, I haven't written stuff out in a while. Let me go ahead and do that. Okay. So if you were to take, I don't know, say g hat, ooh, what happened there? G hat, mu nu, why is this shit? Where does it end? No more pop-ups? G hat mu nu is equal to some conformal factor G mu nu where omega squared of x is positive definite. And you were to write down like the covariant version of the wave equation, if you were to, for the, I don't know, let's take a scalar field phi again, and we were to do something like d mu equal to 0, which is equal to G and then substitute in the transformation of the metric. Well, it'd probably be better if we were to write this instead in the more usable form, but less manifestly invariant, Lorentz invariant. What is it? 1 over root G d mu root G mu nu d nu phi. This is the same equation, just written in a different way. If you were to substitute in how the metric transforms, leave the field alone, leave phi alone, but just talk about how the metric transforms and let that propagate through the determinant of the metric and keep this local, I don't think that that's conformally invariant. I don't see how, because you'd have like product rule. Are they saying that this is... Can someone say, are they saying that this equation should be conformally invariant? Airsofter says it is. Let's take a look at that. Let's check that out real quick. What time is it? I want to give myself a time limit so I don't waste too much time. 3:22. So by 3:30 I want to see. So if we just write let's keep it 4 dimensions, I guess. We can do it in d dimensions, why not? So if G mu nu transforms this way, then G tilde mu nu is equal to omega to the minus 2 G mu nu. And then we also have this determinant of the metric. So we're taking products. If we want to talk about how it scales, we can think about it as if the metric is diagonal, in which case the determinant is just the product of the diagonals. So in d dimension, there's going to be d diagonal components, and each one of those components transforms with the square of that omega. So there would be we would have root minus g hat would transform in terms of, so we're not just taking the determinant of the metric, it's the square root, so that factor of 2 would cancel, so it'd be omega to the d of x times root minus g. And if we substitute this in to this equation, so right now we're in unhatted, so we can invert everything. So that means G mu nu is equal to omega to the minus 2 of x, hence why I said omega squared is positive definite, or I made that definition. So G mu nu has that. That means that root minus g is equal to omega to the minus d of x, root minus g hat. So let's start writing this stuff out. So 1 over root g would then be written as omega to the d of x over root minus g hat times d mu. So I'm doing a transformation of the metric, and I'm leaving the coordinates alone. Let me make sure that what I'm saying so far makes sense. Okay, looks better. Okay, and then we have a root g, which is going to be omega to the minus d of x root g hat. Then we have a contravariant, or the inverse metric, I guess. So then we're going to have an omega squared of x, g hat mu nu, d nu phi. Don't get me wrong, there might be a solution of phi where there's a transformation of phi that leaves this invariant, but I'm saying if I leave that alone, I don't see how this is going to work out. So this is equal to omega to the d of x over root minus g. I'm going to drop the minus sign. You get it. It's pseudo-Riemannian. There's a minus sign that you have to take care of. D mu. So omega to the minus d plus 2 root minus g, g hat mu nu, d nu phi. Okay. Well, first of all, these equations of motion are equal to 0, so I actually don't need to be carrying this stuff around anymore. I can just look at this. So if I take this derivative, this is a function of x. So this is going to do, we have a bunch of product rule. What should we do? Should we make the metric, should we pretend the metric is constant? Or should we keep it general? Let's just apply product rule. Why not? We'll do, so this is going to be minus d plus 2 omega to the minus d plus 1 times d mu of omega root minus g, g hat mu nu, d nu phi, plus omega to the minus d plus 2 d mu root g, g hat mu nu, d nu phi equals 0. We have two different powers of the conformal factor. How is that going to give us something that's... Oh, you're saying just in 2 dimensions. So Airsofter, your claim was it's conformally invariant in 2 dimensions. Okay, I have no issues with that. I'm just saying in general. Damn, how long ago did people say that? Because that would have saved me some time, huh? Oh, it doesn't look like anyone did. No, Prahar did. Okay. Then yes, I agree that this is, I guess, while invariant in 2 dimensions. Gotcha. That's still good to go through, I guess. You can see how, if we go right here, if d is 2, then there's no conformal factor anymore. And then it would be. So this is fine. Okay. I was ready to start throwing hands. Why don't I transform phi in the d equals 2 case? I assume it's because we're doing a transformation of the metric. Right? I think you can do a change of variables for phi that will leave it maybe conformally invariant. Like you can find a solution for phi that will leave it conformally invariant maybe in higher dimensions, I'm not sure. But then you're expressing the equations in terms of a different field. I want to express it in terms of the original field and the transformed metric. Okay. So now we're back. We went through this. They coincide. Symmetries of the Polyakov action. I gave my spiel about covariant derivatives, while invariance. It's simple to see that the Polyakov action is invariant under this transformation. This is a gauge symmetry of the string, and as seen by the fact that the parameter omega depends on the worldsheet coordinates sigma, this means that the 2 metrics which are related by a while transformation are considered to be the same physical state. Okay. So it's talking about like a conformally flat metric, so like FRW or something. Okay. How should we think of while invariance? This is not a coordinate change. Okay. So I'm going to say this, and I want someone to correct me if I'm wrong, because I didn't think, when I was using the terms interchangeably, I see how that would be wrong. So while transformations are actual transformations of the metric, a general conformal transformation can be a coordinate transformation. Is that true? So what did Prahar say? Prahar apparently said something. That is correct. In higher dimensions, you need to transform the field too, and add an additional conformal coupling term to the action as well. That's what I expected. So when Airsofter said that this was conformally invariant, I knew about the conformal coupling. With my research, I always assumed that this wasn't conformally invariant in d dimensions. But as I see now that he was talking about 2. Conformal transformations themselves change the metric, and a subsequent while can undo the metric variation. That sounds like it's suggesting that a while transformation is the inverse transformation for a conformal, which doesn't sound right to me. Conformal transformations include more than coordinate transformations. That sounds better to me. Okay. We're actually moving along. We're getting close to being done. Half an hour left. I don't know if we'll finish it, but we'll be on a good pace for getting to the next lecture next time. This is not a coordinate change, it's the invariance of the theory under a local change of scale which preserves the angles, right? For example, 2 worldsheet metrics shown are viewed by the Polyakov string as equivalent. This is surprising, and as you might imagine, theories with this property are extremely rare, right? If you introduce anything into the theory that introduces a preferred scale, like a mass term or a coupling constant, then I think you tend to completely ruin that kind of symmetry. Almost without exception, right? Get a load of this guy. Alright. It should be clear from the discussion above that the property of while invariance is special in 2 dimensions. I wish that, I mean, I get that this whole time we were working in 2 dimensions, so maybe, yeah, I guess I was just being dumb. But I could have saved myself some time by going to that right away. For only there does the scaling factor coming from the determinant cancel from the inverse metric, right? Because we had that minus d plus 2. If we wish to keep while invariance, then we are strictly limited in the kind of interactions that can be added to the action. For example, we would not be allowed a potential term for the worldsheet. Right. Nor can we add a cosmological constant term. The whole reason for this is then if you do what we just did, you're not going to get a mutual factor of omega to the minus d plus 2. You're going to get something else that's not common, and therefore you'll still have that omega of x dependence. So that's what they're saying is this violates. So if you add this stuff to your action, and then you do the while transformation, you're not going to get the omegas to cancel. Fixing a gauge. Get in its way. Oh no, this isn't a beer. This is just a monster. I have to drive later. I wouldn't drink beer anyways. I'm more of a whiskey guy. Okay. Sorry, that was my research advisor. Okay, we haven't read any of this yet. The equation of motion 1.23 looks pretty nasty. What was that? Oh, okay, it's that thing. Isn't it funny how something can look horrible, but if it looks familiar, it's not as bad? Like, even though it's not any simpler because you've seen it before, the fact that you have seen it before makes it, like, more approachable. Okay. Fixing a gauge. We can use the redundancy inherent in the gauge symmetry to choose coordinates in which they simplify. Since that's like a tensor relation equal to 0, you can choose any coordinate system and it should be valid in all coordinates too, right? Whiskey, especially smoky ones, is great. That's exactly. There's this whiskey from Nashville, Tennessee, from a distillery called Corsair that used to make a whiskey called Wildfire. Is awesome. They changed it. It's still they changed it a little bit. It's called like triple smoke. It's awesome. If you ever get a chance to go to Nashville, I would check that out. Firstly, we have two reparameterizations to play with. The worldsheet metric has 3 independent components. This means the worldsheet metric has 3 independent components. Why is that? What is the worldsheet? Oh, that's the gamma, right? It has 4 components, but it's a symmetric tensor, so one of them is determined by the other. Where the hell is the... Sorry for all the scrolling. I can't stand when I have to watch this stuff, so... Yeah, if we go back here, gamma, alpha, beta, we have the diagonal components are different, but it's a symmetric tensor, so you calculate one, you automatically know the other. So we have 4 components, but only 3 independent. Okay, so that's what that's saying. Half of this video is me scrolling, I swear. Okay, how far do I want to get? Because it could be cool to leave like the last 15 minutes to just kind of shoot the shit a little bit. This looks cool. Actually, someone asked me what's after this, what would I like to delve into after this is all done. I want to look into scalar tensor theories a bit more. It's a bit of an aside, but that's a better answer for what I gave last time. That'd be pretty cool. Okay. This means we expect to be able to set any 2 of the metric components to a value of our choosing. We will choose to make the metric locally conformally flat, meaning the metric is just some conformal factor times the Minkowski metric. You can check that this is possible by writing down the change of the metric under a coordinate transformation and seeing that the differential equations have solutions, at least locally. Okay, so you're not making any statements globally, but at least in our little patch, that works. Choosing the metric of the form 1.27 is known as a conformal gauge. This seems like a very big this seems initially like more than a gauge transformation, because you're saying you have two parameterizations to play with, and you're not just fixing one of the components of the metric, you're saying it is the Minkowski one times, oh, but this depends on the two variables. Maybe that's what it is. Okay, let's just move forward. You can check, we did that. We only used reparameterization invariance to get the metric. We still have wild transformations to play with. Excuse me. Clearly, we can use these to remove the last independent component of the metric and set phi equal to 0 so that it's flat. Looks like we have some conversation about the speed of light in the chat. We can always choose coordinates such that it looks flat everywhere. Oh, that's all it's saying? So it's saying space is still a manifold. Okay. The fact that we can use Weil invariance to make any two-dimensional metric flat. Oh, only in 2D. In 2D. Okay. I gotta keep going back to that. Let's take a quick diversion from our main discussion to see a different proof that isn't tied to the choice of Minkowski coordinates on the world sheet. We'll work in a two-dimensional Euclidean space to avoid annoying minus signs. Okay, so we're going to imaginary time then. Consider two metrics related by a wild transformation. One can check that the Ricci scalars of the two metrics are related by that. I've seen people, for like non-minimal coupling, there's the Ricci scalar in the action. And when applying conformal transformations, I've never found a way to readily transform the Ricci scalar without going with how the metric transforms, and then how that means the Christoffel symbols transform, and thus the covariant derivative. And then you take the commutator, and then that shows you how the Riemann tensor transforms, and then you take the trace, and you get how the Ricci tensor transforms, take the trace again, and then you finally have your transformation rule for the Ricci scalar. I'm not sure if this identity that they're showing right here is... This is probably not a one-liner to prove. Andrew coming on, my apologies, I had a question about Redshift. No, you should never apologize for having a question. I don't care if it's related to what we're doing. That's what's cool about this, is we can just, it's a nice place to interact with everybody. You should never apologize for that. I can get the confusion about 2D, etc. It's weird. Theory is a two-dimensional field theory describing an object in a higher dimensional space, so there are two ideas of dimension all the time. That identity is one of those nice result, terrible derivation. Yeah. Oh, so you're saying if you do it in Riemann normal coordinates, then you don't have to talk about the Christoffel symbols. Well, you'd still have to have the transformation for the Christoffel symbols, because you have to have their derivatives. So it seems like there's still a conservation of effort there. I'm not saying it's terribly hard, but I think it would still be very tedious. It's half the work for Riemann. Okay. The reason, we can therefore pick phi such that the new metric has a vanishing Ricci scalar by simply solving this differential equation. However, in 2 dimensions, not higher. A vanishing Ricci scalar implies a flat metric, right? You got, what did Flournoy say? You got flat, Ricci flat, and the other flat that is so unhelpful it doesn't even have a name, or whatever he said. It's an astronomy question, but this is in your field. Is this in your field? Can you answer it? I didn't really see the question. Maybe I'll look back after in a little bit. I don't know how much farther. We're not going to get much farther than this. We're just kind of reading through because I don't want to. This can get hard for me to picture, so I don't want to rush through it. So this is probably going to be a good spot to stop. Then we get to the energy momentum tensor, it looks like, which will be cool. So we have this. In particular, the symmetry of the Riemann tensor in 2 dimensions means that it must take the form, yeah. Okay. I've seen this before. Something like what is it? You can't get intrinsic curvature in 1 dimension. In 2 dimensions, the Riemann tensor is like proportional to the curvature scalar. Again, probably one of those things that's not the easiest or the most straightforward to prove. And it's also not that rewarding probably to show. But I'll buy that. If you think about like sectional curvatures, if you're reducing the dimensionality of your space, there's only so many sectional curvatures you can talk about. So it's not horribly surprising that in a certain number of dimensions you would get relations like this. Okay, let's go ahead and stop the string theory stuff here. So tomorrow, or not tomorrow, I'm not sure when the next stream is going to happen because soon I'll be driving back to Virginia from New Mexico. So sometime in early September, I imagine we'll do another one of these live streams. But let's kind of shoot the shit a little bit from now on. Let's take a quick look. Nah, we'll save it for next time. I was going to say the exercises, but I think we're good for there. So let me just... Now we are at the webcam. Just the webcam. And I just kind of want to read through the chat a little bit. Why is it not letting me drag the chat? Oh, there we go. Okay. Why bother with string theory? There's no funding for it. I have no interest in doing it professionally. I thought it would be interesting. That result that you can get by proving the Ricci curvature has 1 degree of freedom in 2D. There's then only one thing you can write down that has all the right symmetries and contracts to R. Oh, yeah, because you have anti-symmetry and different symmetry for the various permutations of the Riemann tensor. Okay. It's kind of like, it's like a structure function decomposition where it's like, well, what could it be in terms of? And absorb our ignorance into those structure functions or form factors in elastic scattering. Anyways, if I had a reasonable understanding of tensor calculus and GR, how difficult is it to find resources and teach it yourself? I don't understand the question. So you're saying teach what yourself if you already know calculus, tensor calc, and GR? What courses are you teaching? I'm not. I'm full RA, full research assistant. Oh, I'm not the person to ask what resources to teach it yourself for string theory. I'm in the same boat with you. I'm hoping this works a little bit. The question was, if light from distant galaxies traveled instantaneously towards us and 1/2 c away from us, would the cosmological redshift still occur? The issue with allowing for instantaneous things is if you allow things to move distances instantaneously, then you're allowing yourself to convert space-like events, space-like separated events, into time-like separated events. So real quick, if we go over here, I don't put too much thought into those questions because there's always not a loophole, but a reason why something doesn't work. Like if you write down a line element, let's say d tau squared is equal to dt squared minus dx squared. So we have 2-dimensional Minkowski geometry. Let's forget about GR. Let's just talk about special relativity and say that this is Lorentz invariant. It doesn't matter what inertial frame you're looking at, this is never going to change. So if we're in a frame where events happen simultaneously, so we're saying dt is 0, then in some frame, in frame 1, then we have d tau squared is equal to minus dx squared. But this should be Lorentz invariant. It should happen in all frames. Now dx squared will change in a different frame. It'll be some dx prime that's compensated by a dt prime, but this quantity is Lorentz invariant. You should always still get the same thing when you take the combination. If you allow for things like objects moving somewhere else instantaneously, then what you're allowing is for, so if I'm saying something, there's a frame where things happen simultaneously, then that's called a space-like separated event. If I have a frame where things happen at the same location, then that's a time-like separated event. If you allow for instantaneous movement, like instantaneous transmission, or instant transmission, if we're going to do Dragon Ball, then you are allowing yourself to transform space-like separated events into time-like separated events. So in frame 2, if you were to say, I don't know, if you were to suppose d tau squared, which is Lorentz invariant, is now equal to some dt prime squared, then you reverse the sign of something that's Lorentz invariant by just going to a different frame. And if you calculate the consequences, you start violating causality if you do that. So questions like that where you're like, let's suppose this can happen instantaneously over here, you run into bigger problems than what happens to the redshift. You run into problems like I killed myself before I was born, or stuff like that. So I don't know, I haven't thought about your question, but you're not going to not run into problems like this. If light did travel at different speeds in different directions, well, that's what they searched for. That's what they searched for with Michelson-Morley, right? If you had, if there was a rest frame of the universe that was dictated by some ether, then if you have the speed of light going with the ether, it would be a different speed of light than if you went against it. And then they found that that didn't happen. You get that null result. Anyways. How do you understand cross-sections in terms of quantum field theory? I'm watching lectures and they go into periodic space. I mean, I've made a couple of videos on differential cross-sections. It's a probability, right? It's a probability that something happens. Given an initial state, what's the probability that this well-defined final state is what you measured? It's in terms of scattering amplitudes, and we know how to relate what we calculate theoretically to scattering amplitudes through LSZ, the reduction formula. What time is it? Got 7 minutes. I'm not saying Michelson-Morley has something to do with all frames of reference, but in terms of like it being the speed of light being different this way than this way. The not having or being the same in reference frames is like, it's not a consequence necessarily of Maxwell's equations, but it's suggested by them at least. I think someone mentioned earlier that Newtonian gravity doesn't have time dependence on the potential. Does that answer your question? Yeah, so that allows for action at a distance. Like you put a source somewhere and the other mass immediately feels it. Which isn't really physical. I hope you'll be converted to the primarily positive metric by the end of reading those string theory notes. I mean, I can use both. I mean, I took GR. It was the primarily positive signature. I don't really understand. I don't care what people use. It doesn't really bother me that much. But I think it was... I have this book called Aspects of Quantum Field Theory and Curved Spacetime, and he says something cool where he says, I like my energies to be positive. Like if I act on it with the metric, I don't like getting a minus energy. But having a minus momentum component is just fine, since momentum has directional information. So if you say your form momentum is E and P, and then you apply the metric, one of those has to change signs, and it's a matter of taste whether you like your energy to be negative or your momentum. Which, it's a convention, right? You're going to get the same physical end result, but I like that reasoning. With the minus plus 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 signature, weight rotations become easier to handle. Well, Wick rotations, you're already going to imaginary time, right? You're going Euclidean. I don't understand. Anytime I've used Wick rotations, we always used plus minus minus minus. Because then your wildly oscillatory exponential of the action becomes damped. That's the end result. That's still, maybe it depends on whether you're taking e to the plus or minus integral of the action. Euclidean metric has plus plus plus, which is simple to describe as a Wick rotation of minus plus plus plus. Oh, I see what you're saying. Do I see what you're saying? Because you're going from t goes to plus or minus I tau, and you're squaring that, which is going to give you a minus. Okay, so I do see what you're saying, but you can still factor out an overall minus sign. Why is quantum mechanics written in terms of Hamiltonians, but everything else is in terms of Lagrangians? Well, the Lagrangian formalism of quantum mechanics just gives you the path integral. That's the natural way of doing quantum mechanics using Lagrangians. You can do, like, if you do path integrals, you don't have to do only quantum field theory with path integrals. You can do regular quantum mechanics. If you try to do, like, the harmonic oscillator in quantum mechanics using a path integral, you can do it. It's really hard, but you can do it that way. Hamiltonian formulation of GR. I'm not even familiar with that. Is this the replacement for tensor calc? No, technically the replacement for the tensor calc series is going to be group theory. But I haven't really gotten around to... after finishing the series, I wanted a break from formally teaching something. This isn't me teaching you guys string theory. This is me going through it with you, you know? And it's less... stressful isn't the right word, but it's less demanding. Like, there's no expectations of me understanding it right away, you know, and then being responsible for someone else's understanding of it. And since I understood tensor calculus leaps and bounds better than I understand group theory, because my understanding begins and ends with Lie groups and Lie algebras, and, you know, the fundamental and adjoint representations of the group, you know, I have a lot of foundation to build before I start making formal videos on that. You think Lie groups, Lie algebras would be dry? Yeah, I think it would be cool if you... because you can effectively derive to, well, you can derive all of the quantum field theory structures by thinking in terms of Lie groups in the algebras. Like if you can talk about how like the gauge fields transform in adjoint representation and the matter fields in the fundamental. What do I have to add to my Lagrangians to make it locally gauge invariant for whatever gauge group you're talking about? And seeing if those structures commute with each other or not. You get interesting kinds of self-interactions. I think it could be dry, it could be interesting. I'm not sure yet. If you pull back, your new favorite phrase, to a space-like plane using mostly plus, you get a normal metric. If you do this mostly minus, you get extra minus signs, so geometry tends to prefer mostly plus. I guess that's because Euclidean is plus. Any advice when going through papers? I'm starting to go through cosmology papers, and my professors assigned to me finding it a little bit difficult to keep track of things. I used to have advice for how to read papers. I'm trying to remember what my advice was. I typically have like a OneNote document or a LaTeX document, and I start writing stuff out. It's hard. Eventually, I guess this is the thing. When you start out reading papers, so much of what's in there is completely new jargon to you. And that's something you have to bite the bullet and get through and take notes on the words you don't understand. You're Googling every other word. And then the next relevant paper will have redundancies. It'll have words in there that you looked up last paper that you don't have to look up this time. So at least if you're staying in the same field, it gets a lot easier, but there is just a large learning curve. Victor P says, read the intro, look at graphs and conclusion. Yeah, that's a good place to start. The abstract is horribly dense if you're new to the field. All types of particles come from representations of the Poincare group. Yeah. You have the spin 1 representation of the Lorentz group basically being the photon. Particles, fields, rather than fields, go to particles. Okay. Have I completed House MD? Yeah, I've seen that multiple times over. I think the fact that you can do e to the matrix and get a rotation matrix is neat, even divorced from physics. I remember the first time I saw the exponential of an operator. I was like, what the hell does that mean? Okay. Well, this has been really fun. I think I'm going to have to head out at this part. Someone says, am I still dead set on being a professional researcher? Absolutely. I'm not going through this PhD for nothing. But I'm going to go ahead and finish up the stream now. I appreciate y'all hanging out with me. This has been a lot of fun to go through. And I love having people like Eigenchris here or Airsoft or so many people who can put in their 2 cents and actually help me, because how many questions did I have that I would have been dead in my tracks if it weren't for them. So I appreciate y'all joining. You guys make the stream better than if it was just me making a video on it. So I think I should be doing another one not until probably the 1st or maybe 2nd week of September, just because I'm going to be traveling. But yeah, this has been fun. So I'm going to go ahead and end the stream right about meow as soon as I figure out how that is. Let's see here. And yeah, this will be uploaded on YouTube. So, bye-bye, everybody.